Good morning. When we look at molded devices, we can see several features which are typical. One is the body. Typically, it's made of a black material, which is a thermoset plastic. And that plastic surrounds a lead frame, which is a metal structure, which was made to interconnect the device to the outside and to complete system. When we section such a device, we can see many more features and elements. One is the chip, another is some metal structures, and in that case here we can even see the device that was soldered with the solder joints here onto a printed wiring board. But now let's concentrate just on the small device. And here is another sensor package that is a Hall sensor. Again, here, I change color. Here is the body. Again, that typical black material. In our case, we have embedded it into another material just for preparation, just to make a cut and to handle it. In that material, here we have the metal structure, which is a copper alloy. Here, of course, is the silicon chip, and that is a gold wire. And now, today, we will deal with the materials which are the elements of such a package. Let's start with the metals of the lead frame. The lead frame is made from sheet material, and the most important material is copper alloy. Typically, such copper must be somewhat harder than a normal pure high purity copper. The reason is that such a lead must not bend too easy. It must bend because it's brought into shape, but it must not bend in an involuntary way when it is not desired. And so, for instance, the coplanarity of the leads would be degraded. Okay, so here we have several typical compositions. In many cases, a little iron is alloyed into that sheet, and some of the properties we will still need during that lecture is the elastic modulus, because the elastic modulus will determine the amount of stress we can have in such a device. So typically it's for such copper 120 gigapascal, and copper alloys typically have a CTE, which is a coefficient of thermal expansion of 16 times 10 to the power of minus 6 per Kelvin, or we can also say ppm per Kelvin. In some countries, people also say, for instance, micrometer per meter. That's easy to understand. If we have 1 meter of length of such a material, it will expand for 1, or in that case 16 micrometers when we heat it by 1 Kelvin. Another property which is of high relevance is the thermal conductivity, which is measured in watt per meter Kelvin. And here copper alloys are quite superior to other metals. Pure copper has 400 as a thermal conductivity. Alloying typically degrades the thermal conductivity, but 260 is still a very high value. Also, I would like to mention that these data are always typical data depending on the manufacturer, depending on concentration changes which can be there. There will be a certain scatter in such data. Okay, that's a typical copper alloy which is used very frequently. On the other hand, we have an alloy which consists of iron and nickel. It's so-called alloy 42. And these iron-nickel alloys have a certain property, that is, they expand only very little compared, for instance, to copper alloys or compared to other pure metals. This iron-nickel alloy is somehow similar to a stainless steel, so it has a higher elastic modulus. In this case it is roughly 145 gigapascal, but due to this special alloying effect, it has only a CTE of 4.3 ppm per Kelvin or micrometer per meter and Kelvin. And like all stainless steels, it has a relatively poor thermal conductivity of only roughly 16 watt per meter Kelvin. So when we regard these CTE values, we could say, okay, this 4.3 is a value which is similar to silicon. So if the CTE difference to silicon is low, so let's say silicon roughly has 3, then the stress against silicon will be low. On the other hand, the stress against other elements could be higher. For instance, when we look at the copper, we can say, okay, 16 is roughly what we have in a printed wiring board. That also could have something like 15. So we could say these copper alloys are good or low stress in comparison to printed wiring board features. So the copper iron alloy would be good against the outside features of the package. The alloy 42 would be good against just against silicon. It must be said that in the last years, the trend has strictly gone towards these copper alloys, and the alloy 42 is only used in special applications where very low stress against silicon is of utmost importance. Now let's have a look at the molding compounds. I jump back a little. Here we see these little dots inside the black material. And now the question is, what kind of material do we have here for the molding compound? And why do we have these constituents? And now let's start with constituents in a molding compound. The main constituent is silicon oxide. That's these small dots. Silicon oxide has a very low CTE, around 1. On the other hand, the base of this material is epoxy resin, and that resin has a very high CTE. So bringing together the epoxy and the silicon oxide it will create a material which has a relative low CTE. In that case, we can see, okay, depending on also on temperature, the CTE is somewhere between 8 and 15 ppm per Kelvin. And so the silicon oxide is a constituent in order to adapt the CTE. Such a molding compound also, it has other constituents. For instance, there are silicones in it and waxes. These are important to release it from the mold. So it will, when we mold it into a certain form, we must get it out from the mold and it must not stick. So it's for mold release. And what we must not have in is no chlorine, because chlorine would promote corrosion, and that is very important. Avoid corrosive effects afterwards in the application. Such a molding compound is a so-called B-staged epoxy. B-staged means it is pre-hardened. So imagine we have a resin, we harden it a little, so at low temperature, at ambient temperature, you can handle it as a solid body, but when you heat it, it will, this resin, it will melt again, and then it will proceed to harden. Typically in that B-staged state, it can be stored, for instance, for 2 years at 5 degrees centigrade, or at lower temperatures even longer, but of course a shelf life of 2 years is rarely exceeded. Typically, as I mentioned, when we heat that material, it will be liquid again, and that will happen around 170 to 185 degrees centigrade, and in that way the material is liquid and we can pour it around the body of the lead frame, and then it will harden. This hardening time in the mold form, it is roughly 1 minute to 3 minutes, and then it is, we can take it out from the mold. And after that, we have a post-mold curing time of, let's say, 4 hours at the molding temperature, and that will lead to a stabilization of that material. So if we just have it in the molding form for 3 minutes, it will be hardened, but it's not completely hardened. And the material then would proceed hardening and changing its properties in the application, and that is something which is very undesirable. Okay, then we will see these materials have an elastic modulus which is low compared to the metals, roughly a factor of 10 lower. And also these materials must have a low water absorption. So water absorption is measured in a way, we put a sample of this into water at 100 degrees centigrade for a day, and then we measure the weight, and such materials typically take up 0.1 to 0.5% by weight or by mass. The thermal conductivity is poor. It is a plastic material. the thermal conductivity is increased a little by these silicon oxide fillers, but generally it's not very high. So the heat must come from such a package through the leads and not so much through the plastic body. Another property which is important for high frequency applications is the permittivity. In German, dielectric constant, which is roughly 4 for all epoxy materials, and a dissipation factor of 0.008. That means the dielectric losses in AC applications. An interesting property is in almost all electronic applications, the materials must be inflammable. And there is an American standard, UL is Underwriters Laboratories. That's something like the German TÜV, and they defined such a standard, for instance, standard 94, and in that case we take a strip of that material, we bring it near a flame until it starts burning, still with the flame directed onto that strip, and when we take away the flame, this torch, when we take it away, the flame of the plastic strip must extinguish itself within a few seconds, and that is so-called inflammability. It doesn't say it cannot be burned. It can be burned, but it only is burned with an external heat source, and that's very important. For instance, in electronics, you could have a short circuit, and that short circuit would lead to a flame, to the burning, but after, let's say, a short time, for instance, we have a circuit breaker or something, so we would not heat anymore from outside, and in that case, the material must stop burning, and that's very important for the safety of electronic devices. Okay, so such an epoxy, what is it? Let's talk a little about chemistry. There is a monomeric substance, so that's a pre-substance in these polymers, and that's the so-called diglycidyl ether of bisphenol A. So that's a phenol, and here we have a so-called aliphatic group. It is an ether having that oxygen bridge, and then we have the epoxy group. That triangle where the oxygen is bonded to a carbon here and to another carbon here is not very stable. And so bringing a hardener here will open this bridge, and then we can form bonds, and especially again the oxygen. And in that way, when we bring the hardener here and when we open it, we can form linear bridges, or what is preferred, we can have a three-dimensional network formation of these monomerics. So in the first step, we make linear chains which form the resin. We can also have other chains which are more three-dimensional. For instance, that's a so-called Novolac. Here we can see the phenolic rings are closer together, so we can have other properties of the material. Again, here we have the epoxy group, or here we have still another resin, which also here has such epoxy groups. And in that way, by mixing proper amounts of these resins, we can determine how the network after polymerization looks like. So these are all our possibilities we can go, but the most important substance is this bisphenol A here, and adding certain hardeners will lead to a chain reaction, and then we have so-called macromolecules or so-called polymer.